Solve the non-homogeneous heat conduction problem. So we have a PDE, two boundary conditions, and an initial condition. Okay. If we compare this with the original heat conduction problem, that's the general heat conduction, non-homogeneous heat conduction problem, then in our case R is 1, P is also 1, Q is 0, and this is the non-homogeneous term. We do have that, and we don't have this U derivative part, we don't have that part, and we don't have this part. And initial condition, that's Fx. If we plug U as xt equals x times t, trying to separate the variables because this is a PDE, and whenever we want to solve a PDE, we want to separate the variables. If we plug in, then we end up getting this. In our case, this is 1, this is 0, so R is also 1, so basically this is negative x double prime equals lambda x, which is same as x double prime plus lambda x equals 0, and we don't have this part, and h1 is non-negative, it's a non-zero number, so we have x at 0 equals 0, and we don't have that x prime 1 equals 0. Okay, that's the case. Let me go back here. So as I told you earlier, R is 1, P is 1, Q is 0. The non-homogeneous part, uppercase F, is e to the negative t 1 minus x, and Fx, the initial value, is 0. Then the corresponding eigenvalue problem is x double prime plus lambda x 0, x at 0 0, x prime at 1 0. Now we know how to solve this eigenvalue problem. Then we can find the eigenfunctions. Sine 2n minus 1 pi over 2x, eigenfunctions, and the eigenvalues are just 2n minus 1 square pi square over 4. In fact, when we consider lambda 0 and lambda negative, we get trivial solution. Next, we need to normalize these eigenfunctions. So pretty much multiplying by some constants, and there are still solutions. So let's normalize them. Normalize the eigenfunctions. Okay, check my other videos or look at other work. Then this will be just root 2 times whatever we have earlier. So these are normalized eigenfunctions. Then by the formula, the solution of the original, our given heat conduction problem is just a series, sum of b and t times phi and x, where phi and x are these normalized eigenfunctions, and bn's are found as follows. So bn's are given by this integral by formula that we derived in class, bn times e raised to negative lambda and t plus this integral. Now let's find bn and nu n, then we need to integrate. Okay, these lambda n's are eigenvalues we found earlier, and by formula bn's are found in this way. Bn's are 0 to 1 r times f times phi and x, so r is 1 in our case, and this is initial value, that's given 0, and these are normalized eigenfunctions, but we don't have to worry about anything here. Due to this 0, this integral is 0, and this is true for all n bigger than or equal to 1. So this bn is 0. Now next we need to determine these nu n's. Okay, let's find nu n's. By formula it's also given nu n as a function of t is 0 to 1 f times phi n x dx. Okay, which is 0 to 1. These are non-homogeneous term in the given PD, given heat conduction problem, that is e to the negative t1 minus x times, these are normalized eigenfunctions that we found this, and this integral is with respect to x. So we can pull this e to the negative t outside and root 2 outside. So we have 0 to 1, 1 minus x times sine this. So we got a product, so we need to use integration by parts. This is like u and dv. Do integration by parts and use this fact. Sine odd, okay, odd integer pi over 2, like sine 1 pi over 2, sine 3 pi over 2, that is negative 1 raised to n plus 1. It's like here, this is 1 pi over 2, 3 pi over 2, pi over 2. So negative 1 raised to n plus 1. Okay, and this is e to the negative t. So once we use the integration by parts to this, we end up getting this times e to the negative t, and this is a constant, and I'm calling k star just for this constant, and e to the negative t. Okay, now we have this nu n, go back here, then we can find bn. I mean, that was missing in this solution. The solution is just sum bnt times phi n. Phi n's are already found, normalized eigenfunctions, and bnt is here. This bn is 0, so this part is gone, by the way. Now we need to work on this, and we just found these nu n's. Okay, so here, let me write those. Now bnt, there is uppercase bn, that's 0. So from 0 to t, this is given from the formula, by the way, e to the negative lambda n t minus s times nu n, this in terms of s functions. Okay, in the formula we have nu n as a function of s, but when we find as a function of t. So this will be just this constant e to the negative, not t, negative s ds. Okay, which is, we can pull k star outside and we can separate into two. This is e raised to negative lambda n t, and this integral is with respect to s, so we can pull this out as well. E raised to negative lambda n t, that leaves 0 to t, e raised to negative lambda n s, negative s, so that's lambda n s times e to the negative s. From here and this we can factor s out. In fact, that leaves lambda n minus 1 s ds, and now you integrate and upper limit, lower limit, and we're gonna get k star e to the negative lambda n t. When we integrate, we have to divide by lambda n minus 1, integrate, and upper limit t, so e lambda n minus 1 t minus lower limit after you integrate. Okay, I'm skipping steps. E raised to 0, which is 1, and this is for n bigger than or equal to 1. So we are done. So we basically found bn's in terms of this, where lambda n's are eigenvalues found earlier. K star is here, this whole chunk, and once we have bn, this is bn, so bn times phi n x, and the sum is the solution, final